So we're looking at chapter 7.1, the uniform density function. What is the probability that the package arrives between 10:20 a.m. and 10:30 a.m.? So if we take a look at this horizontal axis, we can see that x is varying between 0 and 60. So let's go ahead and divide that up a little bit. So 30 would be exactly in the middle. We'd have 10, 20, 30, 40, 50, 60, something like that. So the package arrives between 10:20 and 10:30 a.m. means that x would be between 20 and 30 minutes. So we're going to shade the area because the shaded area actually represents the probability. So if we shade between 20 and 30 minutes, we can see that what we're creating is a rectangle. So in order to find the probability, we need to find the area of the rectangle. Well, the area of a rectangle is base times height. So the base is 10, right, because it's 30 minus 20. And the height of this uniform distribution is 1/60th. So the main characteristic of a uniform distribution is that the height is constant, right? So the probability of any equal time intervals would be the same. So 10 times 1/60th would be about 1/6, so about 0.6167. Okay, part B, between 10:45 and 11 a.m. Okay, so 10:45 would be 45 minutes after 10 a.m., so it'd be right about here. 11 a.m. would be 60 minutes. So now I'm going to shade this rectangle, and the shaded area will be the probability. It's a rectangle, so once again, base times height. The base is 15. The height is 1/60th, so that would be equal to 0.25. Lastly, we have part C, between 10 a.m. and 11 a.m. Well, that would be going from 0, 10 a.m., all the way to 60, 11 a.m. So this is the area under the entire probability density function. So the base would be 60, and the height would be 1/60th. When you multiply those together, you get 1. And that just means that the package is certain to arrive between 10 a.m. and 11 a.m. Weights of giraffes are approximately normally distributed with mean mu equals 2,200 pounds and standard deviation sigma equals 200 pounds. Draw a normal curve with the parameters labeled. Okay, so we want to go ahead and draw our normal distribution. The mean always goes in the center, and the mean is 2,200. The first standard deviation occurs about at the inflection point where the curve changes from concave up to concave down, something like that. It's not super important you get it exact, just try to make it somewhat symmetric if you can. The standard deviation is 200, so I'm going to add 200 this way, 2,400, subtract 200 this way. And maybe let's add in one more standard deviation, be the same distance, 200, so 2,600. On the left side, we'll subtract 1,800. Part B, shade the area under the normal curve to the left of x equals 2,100 pounds. Okay, so let's find that x value in the curve. That would be between 2,000 and 2,200, so about right here, 2,100. Shade the area to the left. So that would be going this direction. Suppose that the area under the normal curve to the left of x equals 2,100 pounds is 0.3085. Provide two interpretations of this result. Okay, so what we're being told is that this shaded area is 0.3085. The shaded area under the normal curve has two basic interpretations: probability and proportion. So let's go ahead and write out two interpretations of this area. We'll do probability first. The probability that a randomly selected giraffe weighs less than, and I'm saying less than because we're shaded to the left, weighs less than 2,100 pounds is 0.3085. So that is the probability interpretation. The next one is proportion, or you can think of it as percent. I'll just use the word proportion. The proportion of giraffes, that weigh less than 2,100 pounds is 0.3085. Weights of giraffes are approximately normally distributed with mean mu equals 2,200 pounds and standard deviation sigma equals 200 pounds. What is the probability that a randomly selected giraffe weighs less than 2,466 pounds? So for this problem, and only this problem, I'm going to show you the old school way that this was computed, and it was using a table. I just want you to see that just for reference because we will be using a table in later chapters. This will be the only Chapter 7 problem we'll use a table. Once we finish this problem, I will jump to using a calculator. So we're finding the probability that a giraffe weighs less than 2,466. So the first thing you do is you convert the x value to a z-score. So z equals the x value, 2,466, minus the mean. So this is the z we used back in Chapter 3.4, divided by the standard deviation. So let's go ahead and put that in the calculator. Whoops. So we have 2,466 minus 2,200 divided by, oops, I put the wrong parentheses, divided by 200. Okay, so that's a z-score of 1.33. So we converted the x value to a z-score, so it's the same as the probability that z is less than 1.33. So we want to find the area to the left of 1.33 in the standard normal distribution. That can be done using the table. So if we go to this table, you can see that's already been boxed for us right here. 0.9082 is that probability. Part B, what proportion of giraffes weigh more than 2,466 pounds? So this is the probability that a randomly selected giraffe is greater than 2,466 pounds. We already found the z-score. So the table only gives area to the left. So in order to find the area to the right, we have to subtract using the complement rule. So this would be 1 minus 0.9082, which would be 1 minus 0.9082, 0.0918. But like I mentioned before, you don't really need to know how to use this table for this chapter. Tables will come back later. What we're going to do now is learn how to do this on the calculator. So we're using the same example again with the giraffes. So part A says, what is the probability that a randomly selected giraffe weighs less than 2,466 pounds? Okay, so when we're using a calculator, we do not have to compute the z-score. We're going to do a function in the calculator called normal CDF. The normal stands for normal distribution. Okay. And what it will do is it will tell us the area, but we have to give it 4 pieces of information. We have to give it the lower bound, the upper bound, the mean, and the standard deviation. In this case, the lower bound is actually negative infinity, but there is not a negative infinity button on the calculator. So what we do is we type in the smallest negative number the calculator can handle. Negative 1e99, that is scientific notation for negative 1 times 10 to the 99th power, which is just a very, very large negative number, and that's just our standard sort of stand-in for negative infinity. The upper bound is 2,466. The mean is given, 2,200, as is the standard deviation. So we need to type in all these things into our calculator. You'll see above the variables button, there's this DISTR distributions button that we used in the last chapter. We're going to use that again. So second, vars, and we want number 2, normal CDF. Okay, so the lower bound, I'm going to clear that off so you can see how to type that in. On the -1, make sure you use this negative sign at the bottom. Do not use the subtraction. You'll get an error. Use the negative. Here's the 1. The E is right above the comma, so you need to press second, then the comma button. That gives us that scientific notation that we want, 99. Upper bound, 2466. The mean, 2,200. The standard deviation, 200. Okay, and I'll paste it on your screen for you, and then press enter. Now you'll see this is the same probability we found before, but we did not have to use a table to find it. Let's try part B. What proportion of giraffes weigh more than 2,100 pounds? Okay, so this time we have the words more than, so it's the probability that X is greater than 2,100. All this means is that 2,100 will be our lower bound. So we're still doing a normal CDF, right, because the area represents the proportion as well. The lower bound is 2,100. The upper bound is infinity, but we're going to use 1 E99. This time it's positive 1. The mean and standard deviation have not changed. Okay, so let's try putting this in a calculator. Second, vars, number 2, normal CDF. I'm going to change the lower bound to 2,100. The upper bound is 1, second comma to get the E, 99. The mean and standard deviation are the same. Okay, so the proportion of giraffes that weigh more than 2,100 pounds is about 0.6915. I'm rounding it to 4 places here. Part C, out of a random sample of 1,000 giraffes, how many of them would you expect to weigh between 2,150 and 2,250 pounds? So I want to find the unexpected value. I first need to find the probability, and then we can take that probability, which is the expected proportion, and multiply it by 1,000. So let's find the probability first. So it's the probability that X is between these two numbers. So this time we've been given lower and upper bounds for our normal CDF. Lower bound 2,150, upper bound 2,250. The mean and standard deviation are still 2,200 and 200. So we will do the normal CDF to find the probability. Normal CDF. The lower bound is 2,150. The upper bound is 2,250. The mean and standard deviation are the same. Okay, let's go ahead and press enter. So that is about 0.1974. So that is the probability. To find the expected value, we need to take that probability and multiply it by the sample size, which is 1,000. So 1,000 times 0.1974. 1,000 times 0.1974. So let's just round it up, round it to a whole number, 197. So out of 1,000 randomly selected giraffes, we would expect about 197 of them to weigh between 2,150 and 2,250 pounds. So this is N times P. We discussed that in the last chapter as well. IQs are normally distributed with a mean of 100 and a standard deviation of 15. Determine the 40th percentile for IQs. So if you think back to percentile back from chapter 3.4, that would be 40% getting a certain score or below. So if we drew a normal curve just to kind of visualize what we're computing, we know the mean's in the middle, which is 100. The 40th percentile would be the bottom 40% of IQs. So we know that 50% of them would be less than 100. So 40% would be a little bit to the left of that. So this is an area of 0.4. So what we want to find is this x value that has 40% of the data values below it. And in order to do that, we use the inverse normal function because this time we were given an area. The normal CDF tells us an area. The inverse normal tells us an x value associated with a particular area. So we're going to do the inverse normal function. It needs three things. Area to the left, which we've been given as 0.4, the mean, and the standard deviation. So we find the inverse normal function in the same place we find normal CDF. Second, vars. You'll see that it's number 3. It says inv-norm, inverse normal. The area, you might have this here for tail, you might not. I'm going to leave it default as left because I think some of you may or may not have that on your calculator. So we're just going to leave it as left. So the area is 0.4. The mean is 100. The standard deviation is 15. We're going to leave it as left just in case some of you have that TI-83 calculator. Okay, so press enter and we get an x value. So let's round that to a couple places, 96.2. So what this means is that 40% of people have an IQ of 96.2 or lower. So fortunately, percentiles really lend themselves to the inverse normal in the calculator. Part B is going to be a little bit the opposite of that. What are the IQs of the top 10% of the population? So once again, let's just do a little sketch so we can sort of connect what this looks like to the problem. So we know the middle is 100. The top 10% would be over here on the right tail. I'm going to convert that to a decimal. So I already mentioned before that the inverse normal only works for area to the left. And of course that is depending on what calculator you have, but I'm going to use that as my default just because a lot of you might have a TI-83. So for this problem we were given the area to the right of a particular value. Well, if I know the area to the right, I definitely know the area to the left because I know the entire area under the curve is 1. So if the area to the right is 0.1, the area to the left has to be 0.9. Okay, because I'm using the complement, the entire area under the curve is 1. So this was 1 minus 0.1. So if the area to the right is 0.1, then the area to the left is 0.9. We use the same mean and standard deviation. Let's go back to our second vars, number 3. I think I'll show you both. So for most of you who have a calculator where you can't change the tail, leave it as left. It's 0.9. Okay, so we get about 119.2. That means that people in the top 10% of the population have an IQ of 119.2 or higher. I just want to jump back in here really quick, just in case some of you have the option of changing the tail. I'll show you how to do it. We'd know it's the top 10%. We'd say the area is 0.1 in the right tail. So if you have this option, you may want to go this route. It's going to give you the same answer, of course. It should, otherwise we did something wrong. Okay, so one more example of this, part C. What two IQs separate the middle 70%? So this is a little bit more complicated, so I want to draw a little bit bigger of a picture here. So we're looking at the middle 70%. So I know that 100 is the mean. So I'm going to shade something like this. Okay, so if I've shaded an area of 0.7, that means I have not shaded an area of 0.3. That 0.3 is now divided into two tails of the curve. So if I divide that by 2, I get 0.15. So that is already telling me that the area in this tail here is 0.15. So to find this first x value, I know the area to the left is 0.15. So let me write this over here. Inverse normal, area to the left, mean, standard deviation. And we'll go to the calculator in a second. Now for the upper value, because we're being asked for 2, that separate the middle 70%, If I look to the left of this, I have 0.7 plus 0.15. So for this one, the area to the left would be 0.85. Right, so I'm adding up this shaded area plus this over here. So for most of your guys' calculators, you do have to have the area to the left. So you can type those in. So let's try that in the calculator. Second, vars, do inverse normal. So you might have to do them both separately depending on which calculator you have. Let's try, for those of you that have this version, what the area to the center looks like. And otherwise, you might have to do it a different way, just depending on what you're working with. It should give us 2 values, and it does. Okay, so if you did what I did, you should get 2 numbers. If you don't have that function, you can just do these 2 inverse normals separately in your calculator. So the IQs of 84.5 and 115.5 separate the middle 70% of the population. For this example, we're finding Z alpha numbers. So the reason I'm introducing this notation is because you will see this notation for sure in chapters 9 and 10, and I want the notation to not be super mysterious. So this value here, this notation, Z with a subscript of 0.44, is referring to a Z-score with an area of 0.44 to its right. So that is what that notation means. You could just find that by doing an inverse normal. Remember that the Z refers to the standard normal curve where the mean is 0 and the standard deviation is 1. So the area would be 0.44. That would be on the right, of course, because we're talking about a Z sub alpha. If you don't have the ability to change it to the right, I'll show you what to do in a second. So that would be about 0.15, right? That would be the Z-score with an area of 0.44 to its right. If you don't have the ability to change your calculator to say to the right, you can do to the left, but you have to do the complement. So if 0.44 is the area to the right, then the area to the left is 0.56. And I just got that by subtracting 0.44 from 1. Okay? So then you would still get the same answer, of course. So let's try part B. This time the area to the right is 0.7. So 0.7, I'll change it back to the right. Okay, so that would be a negative Z-score. That means that that Z-score would be below the mean. And one more, Z sub 0.02. That's a very small area to the right. Second vars. Inverse normal, 0.02. So don't get stressed out about this notation. It's just I don't want it to be mysterious when it shows up later. Okay, so it would be a Z-score of about 2.05. Fast food restaurants spend quite a bit of time studying the amount of time cars spend in their drive-thrus. QSR Magazine studied drive-thru times for fast food restaurants and found Wendy's had the best time, with a mean time spent in the drive-thru of 138.5 seconds. Assumed drive-thru times are normally distributed, with a standard deviation of 29 seconds. So there's a couple important pieces of information I want to just highlight here. We have a mean. It's 138.5, so I'm going to write that down. And I have a standard deviation right here. We will need to use those parameters to find all of the answers in this question. So part A says, what is the probability that a randomly selected car will get through Wendy's drive-thru in less than 100 seconds? So this is the probability that X is less than 100. So the probability is the area under the normal curve. So we will do a normal CDF. This is a less than problem, so the lower bound is negative infinity. We use negative 1e99. The upper bound was given as 100. The mean was 138.5, and the standard deviation is 29. Let's go ahead and put this in our calculator. So second, vars, normal CDF, number 2. The lower bound is negative 1e99. The upper bound is 100. The mean is 138.5, and the standard deviation is 29. Okay, so probability would be approximately equal to 0.0922. B, what is the probability that a randomly selected car will spend more than 160 seconds in the drive-thru? So this is the probability that X is greater than 160. So this time we were given a lower bound. We still do a normal CDF. The lower bound is 160. The upper bound is infinity, or we use 1e99. And the mean and the standard deviation, of course, have not changed. Okay, so we type those in. So we go back to our second vars, number 2, normal CDF, which will tell us the area. The lower bound is 160. The upper bound is 1e, so second, comma, 99. And then the mean and standard deviation are not different. Enter. Okay, so the probability is approximately equal to 0.2292. What proportion of drivers will spend between 2 and 3 minutes in the drive-thru? So be careful here. They went ahead and changed the units. Every single other question was in seconds. Here we have minutes, so let's convert 2 minutes and 3 minutes to seconds. There's 60 seconds in a minute, so 2 minutes would be 120 seconds, and 3 minutes would be 180 seconds. So just make sure that you don't let that trick you. The units all of a sudden changed. Okay, so we go back to our normal CDF again. The lower bound is 120, the upper bound is 180, and the mean and standard deviation are the same. Okay, so let me write that down for you here as well. Normal CDF, 120, comma 180, comma 138.5, comma 29. Some of you may need to type that in directly if you don't have that additional menu. So we have 0.6620. Part D, would it be unusual for a car to spend more than 3 minutes in the drive-thru? Why or why not? So remember from chapter 5 that we consider something to be unusual if the probability of it occurring is less than 0.05. So we first have to find the probability. So it says more than 3 minutes, which is 180 seconds. So we're going to find the probability that X is greater than 180 seconds. So once again, a normal CDF. The lower bound would be 180, the upper bound 1e99. The mean and standard deviation are the same. Okay, so we're going to find this probability and compare it to 0.05. So we're doing a normal CDF. The lower bound is 180. The upper bound is 1e99. The mean and standard deviation are the same. 0.0762. So now we have to answer the question, would it be unusual? Well, the answer is no. And that is because the probability is greater than 0.05. And that is always the default we'll use. The reading speed of 6th grade students is approximately normal, with a mean speed of 125 words per minute and a standard deviation of 24 words per minute. What is the reading speed of a 6th grader whose reading speed is at the 90th percentile? Okay, so just want to reiterate, some of you have the option of changing the tail area, left, center, right. Some of you don't. I'm going to write it down as if you don't, all right, just so that we can all use the same thing. So in this case, it's a percentile, so that would be the area to the left, so that is perfect. So we're going to do an inverse normal. The area to the left is 0.9. The mean is given as 125 right here. The standard deviation is given as 24. So second vars inverse normal. So the area is 0.9. The mean is 125 words per minute with the standard deviation of 24 words per minute. I'm going to leave it as left because I think most of us might not even have that option, and left is the default. Okay, so that would be about 155.8 words per minute would be the reading speed of a 6th grader whose reading speed is the 90th percentile, meaning that 90% of 6th graders read at the same speed or lower. B, a school psychologist wants to determine the reading rates for unusual students, both slow and fast. Determine the reading rates of the middle 90% of all 6th graders. What are the cutoff points of unusual readers? Okay, so let's draw this one out because it's slightly more complicated. So remember that the middle is the mean, 125. And it says the reading rates of the middle 90%. So I'm going to shade in the middle. Try to make it somewhat symmetric. So this shaded area is 0.9. That means that the areas that I have not shaded in the tails should add up to 0.1. Right? Because the entire area is 1. There are 2 tails. That means the area in each tail is 0.05. So now I have, first of all, found the area here. To the left of this x value is 0.05. So I can do an inverse normal with an area of 0.05 to the left with the same mean and standard deviation. When it comes to this one, right, because it's asking us for 2 scores that cut off the middle 90%, the area to the left would be 0.9 plus 0.05, so 0.95. Okay, so I'm going to go ahead and go in the calculator. So some of you might have to do 2 separate inverse normals like I wrote right here. Some of you might have the same calculator I do, in which case you don't have to do that. You can do the center. So I'm going to do that on the calculator, but do whatever is right for the calculator that you're using. This is just faster for those of us that have it. Okay, we would get 2 values. So 85.5 or 164.5. So what this means is that the unusually slow readers would read 85.5 words per minute or fewer, and the unusually fast readers would read 164.5 words or more per minute. Ball bearings are manufactured with a mean diameter of 5 millimeters. Because of variability in the manufacturing process, the diameters of ball bearings are approximately normally distributed with a standard deviation of 0.02 millimeters. Any ball bearings that have a diameter less than 4.95 or greater than 5.05 millimeters are discarded. What proportion of ball bearings is discarded? Okay, let's draw it first so we can sort of figure out what it's asking us here. We know that manufacturing isn't perfect and some of the ball bearings are just too far off from what they're supposed to be, that they have to be tossed out. Okay, so the mean in the middle is 5. So it says any ball bearing with a diameter less than 4.95 is discarded. So that's over here. So I'm shading the area of the discarded ball bearings, or greater than 5.05, that's over here. Okay, what proportion of ball bearings is discarded? There's 2 ways to do this. You could find these 2 areas separately doing 2 normal CDFs and add them together, or you could find the area in between them and subtract it from 1. And I think I'm going to go that route because it's a little bit quicker. So that would be 1 minus a normal CDF with a lower bound of 4.95, upper bound of 5.05. The mean is 5 and the standard deviation is 0.02. So I'm using the complement rule to sort of make this faster for me. So 1 minus a normal CDF, 4.95, 5.05. The mean is 5 millimeters. Standard deviation 0.02. Okay, so it's about 0.0124. So they have to toss out a little bit more than 1% of the ball bearings that are manufactured. Part B, if 30,000 ball bearings are manufactured in a day, how many should the plant manager expect to discard? Okay, so this is an expected value. So we take the sample size, and you multiply it by the probability, which is the same thing as the expected proportion. So 30,000 times 0.0124. So if they make 30,000 ball bearings, they will probably have to discard about 372 of them. If an order comes in for 50,000 ball bearings, how many bearings should the plant manager manufacture if the order states that all ball bearings must be between 4.97 millimeters and 5.03 millimeters? So whoever's placing this order is slightly more strict with how they want their ball bearings. Their standards are a little bit higher than the plant itself. So let's start off by drawing what ball bearings they would be keeping in terms of this normal curve here. It's not a very good one. Okay, so the mean is 5. 4.97 is over here somewhere. 5.03 is over here somewhere. So the order wants 50,000 ball bearings between those two values. So let's find that proportion. What proportion of ball bearings actually fall between those two values? So we'll do a normal CDF. The lower bound is 4.97, the upper bound is 5.03, the mean is 5, and the standard deviation is 0.02, so that's second. Bars number 2, normal CDF. Type it in. So the proportion of ball bearings that meet that standard is about 0.8664. So we want 50,000 that are between those two numbers, which means we need to make more than 50,000 because we know that some of them will not meet that standard. They'll get discarded. The question is how many more than 50,000? We don't want to make too many because that would be wasteful. But if we don't make enough, then we haven't met the order. So here's where we need a tiny little bit of algebra. So we want to say 0.8664 of what number will give us 50,000 that meet the requirement. So we don't know how many, but we know that however many we make, about 86% of them will meet the standard. So we have a little equation here. To solve this, we divide. Right, to undo multiplication, we divide. So in a calculator, I'll do 50,000 divided by 0.8664. Okay, now even though it's 0.06, I'm going to round up because I don't want to not make enough. So by default, no matter how tiny the decimal is, for a problem like this, it's safer to round up to the nearest whole number. So 57,711 ball bearings should be manufactured to make sure that we have about 50,000 that meet the standard of being between 4.97 and 5.03 millimeters.